Okay, so we've all dealt with interference. It's kind of a common thing these days because we rely on so much wireless stuff, okay, anymore. So you've probably all had something crap out on you wirelessly, okay, at some point because it was being interfered with, okay? Although things are getting better now. I remember when we first got like Wi-Fi, it was on the same frequency. This would be like the wireless A. Where we are now, like G or something, okay? But the first wireless stuff was on the same frequency as your microwave. So if you fired up the microwave and were in any vicinity near the microwave, the Wi-Fi would go up. Okay? It was like highly inconvenient, okay? Especially if you're watching like the first round of the NCAA basketball tournament and you've got like, 4 games going on different devices, the laptop, the iPad, phone, TV, okay? And then the kid comes in to microwave something to eat, and all of a sudden, because it's crunch time in all of those games, and the Spartans are in overtime, shots going up, and you freak out because suddenly all the screens are blank, and yeah. So, and you're yelling at your kid for making popcorn. But that never happened in my house, ever. Okay, so what happens is waves try and occupy the same space at the same time. They can do that because they're energy, okay? They're not matter. Matter tries to occupy the same space at the same time. That's impossible, okay? But waves can. And even though they're traveling through a medium, okay, they can make the medium take the shape that would be represented by their combined energies, okay? That's what causes interference, okay? Rather than getting waves that are properly shaped and that would transmit a proper wireless signal for you, okay, you get a jumbled mess of waves that are the combined energy of the 2 interfering or 3 interfering waves, okay? And that can't be translated by any device, and it just ends up being signal loss, okay? So that's kind of what happens when waves interfere with each other. Sometimes we can make interference work for us to amplify things, okay? And sometimes we can make it work for us to quiet things, okay? It all depends on the application we want to have. If you have true noise-canceling headphones, okay, those use interference to quiet the sounds outside of the headphones. All right? So what a true noise-canceling headphone has on it is it has a microphone on the outside of the headphone. Okay? That microphone obviously detects all the ambient sounds in the area and then tells the speaker in the headphone to make the exact opposite waveform so that it will cancel out the waves that are ambient around you. Okay? Hence, canceling the noise, okay, from around you in that area. Okay? That's how a true noise-canceling headphone works. You gotta watch yourself if you're buying them online, because sometimes they're just like well insulated against sound and they're not true noise-canceling headphones. True noise-canceling headphones involve a microphone and a microprocessor and the production of actual counter waves, okay, in order to make sure those sounds are gone. That's also how electronic warfare countermeasures work. Okay, so if you've ever heard of something being jammed, okay, a radar being jammed or something like that, okay, that is the result of creating a bunch of waves in an area that would interfere with the existing radar or tracking systems or whatever, okay, in order to make something lose a lock or a target acquisition on it. Okay, does that sort of make sense? Okay, so all of those are kind of different applications of interference. All right, so understand what happens when 2 waves occupy the same space at the same time. That's interference. Okay, learn the 2 types of interference. There are only 2 kinds. Okay, and understand how those can be applied to practical uses. It's funny because it's true, but probably not. All right, anybody in here able to hear a dog whistle? Okay, some people can. Okay, it's pretty rare, okay, but some people can. Reason we can't hear it, it's too high pitched or too high frequency. The wavelength is too short and our eardrum can't vibrate back and forth fast enough for us to hear it. Okay, it's not a matter of interference, it's just our eardrum isn't designed to hear that high a frequency. Okay, dogs' eardrums are obviously better, okay, or different, and they can hear higher frequencies of sound. So when you blow on a dog whistle, you don't hear it, okay? But your dog squeals, okay? Because it hurts their ears, because they can, okay? And it can be quite piercing for them. All right, so straightforward way to deal with situations in which two or more waves pass through the same space simultaneously. So if we're looking at the two different kinds of interference, this is what it looks like diagrammatically. I'm actually going to show you a video we did of it, okay, with the slinkies on the floor, all slowed down and everything, so you can see it very clearly. Okay. In the first situation, I've got two pulses that are up, or what we would call in phase with each other. Okay, they're in phase because they're both doing the same thing. Okay, so when they travel towards each other, energy is traveling through the medium. When they get to the same point in the medium, that energy combines, okay, and it creates a greater amplitude, because the energy has to be conserved and it has to be represented by the motion of the slinky, okay, or whatever the medium is that it's traveling in. Okay, so the slinky will take this shape when those two crests are completely overlapping, right? The previous amplitudes, we'll say, were like +1 and +1. So what's the amplitude here? +2. Okay, that's what we call the principle of linear superposition. Okay, in other words, what happens to the medium when two waves are in the same place at the same time? We add their amplitudes together. Okay, pretty straightforward. Okay. And then, after that, they go on as though nothing happened. Because remember, waves are energy, not matter. It's not like when two particles try and occupy the same space at the same time. They crash into each other and then their paths are altered and whatever else. But with waves, they can just pass right through each other, okay, like ghosts, and have no problem going on after that. Because again, they're not matter, they're energy. Okay, so they go on completely unaffected after they interfere. So that means then that interference is also localized. Okay? If anyone's ever had like their phone kind of like, wigging out on them or whatever, and you move away and suddenly it's better, okay? It's just because there was some source of waves that was right at that location that was interfering with it, okay, and causing you to have bad reception or interference there. But as soon as you moved away from it, those waves weren't occupying the same space anymore. Okay, it's usually something localized, like a microwave or something like that, that would cause that. Stepping away from it, okay, makes it kind of go away. All right, so this is what we call constructive interference. Okay, and that's because the amplitudes create a larger amplitude. In the second situation, I've got one wave that's up, or has an amplitude of +1, okay, and I've got another wave that's down, okay, and has an amplitude of -1. So when they come towards each other and try and occupy the same space at the same time, they cancel out. Is the energy still there? It is, okay? Because once they pass through each other, it'll be just like the previous example, and they will go on about their business as though nothing ever happened. Okay? But while they are occupying the same space at the same time, we add their amplitudes together, which causes it to cancel out. That's how noise canceling headphones work. Okay, they create the exact opposite waveform or waveforms so that the waves experience complete destructive interference. Okay, and thus their amplitude becomes 0 or close to 0. Okay, certainly less. Okay, if I had a wave that was +2 and a wave that's -1, okay, and they overlapped, would it still be destructive interference? Yeah, it would be. Their amplitude is still going to decrease. The overall amplitude will now be +1, but they're still canceling each other, at least partially. Okay, so anytime the amplitude is diminished, okay, or the waves are what we call out of phase, okay, then we have destructive interference. All right, I'll show you the video we did here. Take away mine. Hey, this might not be the one I think it is.
One, two, three. Okay.
That was my voice. Did you see that Mr. Dickey changed the name of this? He's trying to take credit for my video. Okay, so if we back up here, right to the beginning, okay? Here's the two big waves coming towards each other, okay? And you can see here that as they try and occupy the same space at the same time, okay, for an instant the amplitude is nearly zero, and then they continue traveling on their way after that. Okay, everybody with me there? I don't know what happened to my constructive interference video. Now it's gone. Hey, is that making sense? It's always good to see it actually happen in slow motion. When I do it on the floor here, it just happens so fast that you just can't get kind of a good idea of it. All right, so this is what we were talking about here. Okay, so on the left, okay, we would be looking at an example of constructive interference. Okay, and on the right here, this would be destructive interference, because the waves are going to cancel each other out, okay, and then again go on completely unaffected after that. Okay, so the principle of linear superposition is this. Okay, the slinky will assume a shape, okay, or the medium, doesn't have to be a slinky, okay, the medium will assume a shape that is the sum of the shapes of the individual pulses. All right, and this is what happens, okay, at the shore, okay, of the ocean. You got waves coming in, they get to the end of the water, they actually reflect off the shore and they go back, which is why every once in a while, okay, it looks like there's nothing going on and then a big one rolls in. Okay, well, that's because some of the wave energy that's going back interferes with the wave energy that's coming in, and every once in a while you get a big wave, every once in a while you get nothing. Okay, it all depends on, you know, the rate at which they're reflecting and how much energy is reflecting back. Okay, everybody all right with that? Okay. Okay, so that used to move, but now it doesn't. Okay, so opposite pulses overlap, okay, then they're going to momentarily cancel. The slinky will appear straight, just as we saw in the video, okay, and again, the resultant pulse or the resultant shape is going to be an example of the principle of linear superposition. All right, so if we have more than one wave, in the examples we just did, it was just one pulse, like it was easy to see. Okay? But most of the time you've got lots of waves trying to occupy the same medium at the same time. So if I've got this waveform here, wave A, okay, and it's trying to occupy the same space as wave B, is that going to be constructive interference or destructive interference?
Constructive.
Constructive, because they're in phase. Okay? And what we mean by in phase is when B is up, A is up. When A is down, B is also down. Okay, so the waves are in phase. In this case, they have the same wavelength, okay, and they're oriented the same way. Okay, so they will interfere constructively, and they will make a waveform that looks like this. Okay, and the resulting medium will have that shape. Okay, it will have the sum of the two pulses. Joe?
What if they don't have the same wavelength? Then wouldn't it be constructive sometimes and destructive other times?
Yeah, it's just not, it's going to be a jumbled mess,
Right.
is what it's going to
Okay.
be. But yes, there will be, yeah, all these like all over the place kind of waveforms that are impossible to decipher.
Okay.
Right? Which is why if you had something that was depending on a wireless signal and that's what was going on, it would just say no signal. Which isn't really true. There is a signal, it just has no idea what it is because it's a jumbled mess instead of a nice and sinusoidal wave pattern like it's expecting. Okay, now in the second one here, okay, when wave A is up, wave C is
Down.
okay. So this is going to be destructive interference, but not complete destructive interference. If it was complete, this would be straight line, just be flat. Okay, in this case, it's diminished. Right, so we have a lower amplitude, okay, but it's still the sum of the individual pulses. This would be like +2, and this would be -1, so my resulting amplitude is +1. Okay, and so on and so on. So we always add the amplitudes together to get our resulting waveform. Okay, now, I always have a question about this on the unit exam. Okay, always, always, and it's like the easiest question in the world, right? Here's how it looks. So I give you like a piece of, like a little bit of like graph paper looking stuff on the test, okay? And what I put on there is, I say, draw the resulting waveform. Or these two waves are occupying the same space at the same time. Draw the resulting waveform and tell me whether it's constructive or destructive. And then I would have something like this. Okay, what would the resulting wave look like?
Green. Like bigger.
Bigger than the purple one? Okay, so like, now, if there was graph paper, would you actually like count
Yes.
the number of lines? Not like what I just did there, which is definitely not the sum of those two things, but okay, you get the idea. And if it was flipped, if the red one was the other way, then we would subtract them, okay, or still add them together, but one's negative, and we would get the resulting waveform. All right, is that like a pretty easy question? 3-mark question on your unit exam. Like I kid you not. That question's on your unit exam, it's 3 marks. You draw the resulting waveform, that's 2 marks. You tell me whether it's constructive or destructive, that's 1 mark. Okay, like it should be the easiest 3 marks you've ever got in physics, is to draw the picture. Okay. All right, now, interference is rarely that simple. Okay, when we get into standing waves, we're going to find that the wave patterns that make standing waves, that make musical notes, that do all of that kind of stuff, are going to be more complex than that, but they are the result of linear superposition and interference. Okay, so if waves are exactly in phase, they'll exhibit constructive interference. Now, this is a 2-dimensional situation. What we just did a second ago was a 1-dimensional situation. All right, so if I've got this person and they're in this situation here where they're standing in front of 2 speakers and the speakers are just emitting a constant tone. Okay, so they're not playing music or anything, it's just a tone, all right? Like a dial tone, like that kind of tone, okay? And they're just playing the same tone. If this person stands equidistant from both speakers, okay, and that distance happens to be 1, 2, 3 wavelengths from each speaker, is he going to hear a sound that's louder than is actually being produced or quieter?
Louder.
Louder, why?
Because it's constructive.
Because we've got a situation where we have constructive interference. Okay, the waves are meeting condensation to condensation, okay, or compression to compression, because they're sound waves. I mean, we can say crest to crest if we want, but we know they're sound waves, they don't have crests and troughs. Okay, so at that point there, he would hear a loud sound because of constructive interference. And if we were standing in a room where this was going on, okay, would there be areas where there would be louder and quieter sound? Yeah. Definitely. Okay, if I was just wandering around this room with these 2 speakers playing a constant tone, okay, if I stood here, would I hear a loud sound or a quiet sound? Loud. Okay, what if I stood here? Quiet. Okay, and what if I stood here? Loud. Okay, because they didn't draw in the other part of the wave, right? Like if they did that, it would be like, you know, that would be the trough in between the 2 crests. Okay, so that would also be a point of constructive interference. They just didn't draw in the troughs. Okay, everybody okay with that idea? So if this was a movie theater, would there be seats in the theater that would suck?
Yes.
Absolutely, okay, because you'd have dead areas, okay? That's why no good theater has 2 speakers, okay? They got speakers everywhere, right? They got speakers up the side walls, up the back, in the front, okay? They're creating that surround sound, and they're usually set up so that the speakers will actually have delay so that you're getting the same sound from all of the speakers, and then it eliminates any points of destructive interference.
What would you say the best theater seat is?
Middle, like dead center is your best bet. Because at the front, you're too close to some of the speakers and the screen. Okay? And that's uncomfortable if you're old like me. Okay? But yeah, middle is definitely the best because then you get all of the speakers acting kind of on you equally. Okay? Second to that would probably be nearer to the back. Okay? Again, in the middle. Anything on the sides is your worst position. Front and sides would be your worst places to be. Okay, everybody all right with that idea there? Okay, let's see if we can replicate that a little bit. Okay, so if I've got these 2-dimensional wave patterns, then I'm going to have these areas of constructive interference and destructive interference, okay, located throughout the room. That's not usually a problem if you're dealing with like a movie theater or, you know, or a home theater setup or something like that, because they don't emit one constant tone. Okay? You only really notice that if you're only playing one constant tone, and then there are definite spots. If you're watching a movie, it's all kinds of different frequencies and things like that, so you don't really notice if there's a dead spot in one particular point. Okay. All right, if we're looking at destructive interference, okay, then I have to change the position of the speaker. Okay? How many wavelengths back do I need to move it if I want them to have complete destructive interference? Half a wavelength, because that's how far apart a crest and a trough are. Okay? So if I back up one of these speakers a half a wavelength, which in this case happens to be a half a meter, okay, now when this person is standing here, he's going to have a crest or a compression meeting a rarefaction, okay, and hear nothing. Okay? If this was a perfectly acoustically perfect room or an anechoic chamber, has anyone ever seen one of those? They're a little wild looking. Like it would look like you're inside a meat grinder.
Oh, it has like spikes and
yeah, it looks like spikes. It looks like the inside of a meat grinder. Okay, and if you stand inside of it, there's no echoes because there's no flat surfaces for the sound to like bounce back to you off of. Okay, and so you don't get any echoes in the chamber. It sounds a lot different. Have you ever heard a recording of yourself? Okay, it's kind of more like that. Like I hear that all the time because I play something and it's like, oh God, those poor kids. Okay, I have to listen to that all the time because I think I sound different than I sound when I'm recording. Okay, and the reason for that is I hear myself in my own sinuses and bouncing off the walls of the room. Okay, it alters the sound slightly, and so I sound to myself different than I actually sound to you. All right, so in this case, we would have complete destructive interference because now the waves traveling from this speaker are traveling 3.5 wavelengths, and these ones are only traveling 3 wavelengths. So what determines whether you hear a loud sound or a quiet sound is the number of wavelengths from the source to the observer from each speaker. If the difference is a half a wavelength, then you're going to get complete destructive interference. Okay? So if this was a half a wavelength and that was 1 wavelength, it would be destructive. Okay? If this was 4.5 and 3, it would be destructive. 5.5 and 3, destructive. As long as the difference, as long as when you subtract them you get something 0.5, it's going to be compression to rarefaction, and you're going to get complete destructive interference. Okay? Everybody all right with that idea? Okay? If it's a whole number, okay, so if this one was to be traveling 4 wavelengths and that one 3, then what would I hear? I'd hear loud, because they'd still be arriving in phase. These ones would have traveled a full wavelength further, but they're still coming together, crest to crest, trough to trough, and interfering constructively. Okay, so what the key here is the difference in the number of wavelengths traveled. Okay, if that's a whole number, 1, 3, 10, 200, okay, they're going to be constructive interference. If it's a half a wavelength, so 1, 2.5, or 1.5, 2.5, 10.5, 200.5, okay, then it's gonna be destructive. Okay, everybody all right with that? Okay, so that would mean then that this point right here would be a point of destructive interference. This point here would be a point of destructive interference. Okay, this point out here would be a point of destructive interference because from this speaker, they've gone 1 wavelength. From this speaker, they've gone 1, 2.5 wavelengths. Okay, difference in travel is 1.5. Okay, this point here, it's gone 2 wavelengths from speaker B, but 1, 2, 3.5 from speaker A, so it's a half a wavelength out. Okay, and we're going to get destructive interference. Yeah.
Does it have to be exactly a half to be destructive?
Yes, completely destructive. If it's somewhere in between, then it's going to be like a smattering, basically. So you'd never get a problem where it was like 0.33, because then what is it? I don't know. It's a little bit of both. Not a fair question then. Okay. So if I gave you a question that gave you numbers like that, it would be it's either a full wavelength or it's a half a wavelength. Okay. Now, it's actually kind of tricky to set that up. So if you got like, 3 wavelengths from one speaker and you got 2.49 something, is that 2.5?
Yeah.
Close enough? Be completely destructive? Yeah. Okay, so again, this is kind of what we've been talking about. Okay, in general, the important issue is the difference in the distance traveled by each wavelength in terms of number of wavelengths, not meters. Okay, it's the number of wavelengths traveled in each situation. So at this point right here, okay, where this orange dot is, the wavelengths have traveled 1, 2 wavelengths from that speaker, and they've gone 1, 2, 3 wavelengths from that speaker. So that would be a point of constructive interference. The difference is 1 full wavelength. Okay, but this position right here, okay, the waves from this speaker have gone 1, 2.5 wavelengths, but from this speaker they've gone 1, 2, 3 wavelengths. 3 minus 2.5 is 1/2. Okay, so that would be a point of destructive interference. Everybody okay with that? Okay, I want you guys to copy this one down. And we're going to run through it as an example. Because I always put one like this on the unit exam as well. Okay, so a question like this actually gets you to do a couple of things. It asks about interference, obviously, but it also makes you do a universal wave equation question. Okay? And I could even make it have more wave stuff in it if I told you that the temperature of the air was a certain degree Celsius, and you'd have to use V equals 332 plus 0.6 T, okay, as well. All right, but in this particular situation, they told me the speakers are 3.2 meters apart, so if I'm drawing a diagram, I separate them by 3.2 meters, and the observer is 2.4 meters directly in front of one of the 2 speakers. Okay? Then they tell me that the speakers are playing identical 214 hertz tones. Okay, so they're telling me that the frequency here is 214 hertz. They're telling me the speed of sound is 343 meters per second. Okay, and then I've got the diagram as well. Now, if that person hears a loud or quiet sound, that's dependent on the number of wavelengths traveled from each speaker. So what should I calculate first? Wavelength. Yeah, if I'm going to calculate the number of wavelengths from each speaker, I need to know what one wavelength is equal to. And I can calculate that because I've got the universal wave equation. Okay, so I'm going to go V equals F times lambda. Okay, I'm going to divide both sides by F. Okay, so I'm going to go 343 divided by 214. I think it comes out to 1.6. Okay, so one wavelength is 1.6 meters. So could I calculate the number of wavelengths between this speaker and the person?
Yeah.
How? You're right. How?
Dividing 2.4 divided by 1.6.
Exactly. Take 2.4 and divide it by 1.6. If each wave is 1.6 meters long, that'll tell me how many wavelengths there are. Okay, well 2.4 divided by 1.6 should give me 1.5 wavelengths. Okay, so to calculate that, I just went 2.4 meters divided by 1.6. Okay, that gave me the number of wavelengths. Okay, now I need to do that for here. What do I not know yet? Yeah, I don't know how far that is. Can I find it? Okay, so I got to do a little bit of Pythagorean theorem. Right? Well, that's not terribly difficult. Okay, so I'm going to go square root of 3.2 squared plus 2.4 squared. All right, so that side's 4. Nice. Okay, so this side's 4 meters long. And if I want to find the number of wavelengths, okay, then I'm going to go 4 divided by the wavelength, 1.6, okay, and that should give me, is that 2.5? All right, so there's 2.5 wavelengths here, there's 1.5 wavelengths here. Does that person hear a loud sound or a quiet sound? Loud. Okay, because 2.5 minus 1.5 is 1, which is a full wavelength. Okay, so really what's happening here is this. Oh, I erased everything. No. Okay, so okay, I've got 1.5 wavelengths from that speaker. And 2.5 from that speaker. Are they arriving at the same point in the wave?
Yes.
Absolutely. That's constructive interference. Okay? It's the difference in number of wavelengths that determines constructive or destructive interference. Okay? In that case, we went 2.5 minus 1.5. The difference was 1 full wavelength. Okay? Everybody all right with that? Okay? There'll be a question just like that on the unit exam. I promise. Okay. Okay, there were a few more of the universal wave equation problems I wanted you guys to work on here. Let me call them. What is going on? You can play that game. All right, I would like you guys to do question, we didn't do question 2, so I'd like you to do question 2. Okay, and actually 2 to 7, because we started on 8 last week. So, okay, from 2 to 7, please. Yes, let me get that. Okay, so the hiker slips and falls into a deep valley, okay, and the rock face that the echo is coming off of is 685 meters away. The partner hears the echo of the scream 4 seconds later. How long did it take the sound to go 685 meters? 2 seconds. Okay, so we're looking for the speed of sound in air. That's going to be V equals D over T, okay, which is going to be 685 divided by 2, which is going to give me 342.5, but I only have 3 significant digits. So 343 meters per second is the speed of sound in air on that particular day. Okay, the wavelength of the sound is 0.750 meters. What's the frequency? All right, V equals F times lambda. Okay, they just told me the wavelength, 0.75. I calculated the speed in part A, so I'll use that. Okay, so the frequency will be 343 divided by 0.75, which should give me my 457 hertz. Okay, everybody all right with that? All right, and then the last thing, what's the period of the wave? Well, I could do this and go V equals lambda over T, plug in numbers again, or I could just go T equals 1 over F. I don't know that there's one that's more or less work than the other. It's one step in either case. Okay, and just go 1 over 457, which should give me 2.19 times 10 to the minus 1? No, minus 3 seconds. Okay, for the period on that one. Okay, so you have choices on that. Okay, that's a pretty typical exam question actually for like echoes and those kind of weird word game tricks that I was telling you about last week. Any other ones? Okay, remember that on some of these questions they are talking about light waves. Okay, anything that's an electromagnetic wave, okay, or a radio wave or anything like that, okay, that it travels at what speed? Speed of light. 3.0 times 10 to the 8 meters per second. That's on your formula sheet on the back. Okay, and remember that megahertz are millions of hertz, kilohertz are thousands of hertz. Okay, so if you see kilohertz, okay, or megahertz, then you've got to put them in scientific notation for hertz. Okay, and do the multiplication as prescribed. Okay, give you a few more minutes here. Okay, so we're told the frequency is 9.95 times 10 to the 7 hertz. Okay, we're told the speed is 3.0 times 10 to the 8 meters per second because we're told it's a radio wave. This is a form of electromagnetic wave. Okay, we're looking for the wavelength, so lambda equals V over F. Okay, so 3 times 10 to the 8 divided by 9.95 times 10 to the 7 should give me 3.02 meters in length. Okay, just gotta make sure.
I don't know how I messed that up then, because I was getting way more answers.
Okay, were you enclosing everything in brackets in the calculator?
No.
Okay, that would be why. Gotta do this 3E8 in brackets divided by 9.95 E7. Then you get 3.02. Okay, if you don't enclose them in brackets, then it assumes everything after this is part of the exponent.
Oh.
And that's a much different number.
Yeah.
Yeah.
Okay, that makes a lot more sense then.
Okay, yeah. Any other ones? How many people are done up to 7? Okay. All right, are these ones making some sense? Okay, not too bad with those. All right, I don't have the Chromebooks, but you have your phones. You can work on your pendulum lab a little bit if you want to get that done. Okay, because that's due on Wednesday. So you got a little bit of time if you want to as well.